Hello, this is Dr. J here with the next episode of my Commander X16 devlog. It's the moment we've all been waiting for. Time to start putting together a library to simplify our development of X16 games. As a reminder, I am assuming that you already have basic knowledge of how to interact with the Vera, VRAM, and HiRAM, and manipulating sprites and tiles with C. So if you're not comfortable with any of those topics, I recommend working through the tutorials I mentioned in the last couple of videos if you're interested in doing your own development on the X16. The first thing our library is going to need is a name to refer to it by. I've created a library for my past indie game projects and I called it Exist, spelled X-I-S-T just to be quote-unquote cool. So, in the spirit of making a similar library just for the X16, I'm going to call this one Exist16, and use the same 1980s Prism-style color scheme for the logo. So, in order to make games on the Commander X16, we're obviously going to need the ability to load images into the X16's memory for display. Now let me go ahead and give a quick reminder on how images are formatted in the X16. Images on the X16 and other such retro-style computers and consoles use indexed graphics, meaning that they have a color palette and each pixel in an image is an index into this color palette. Now, because we want to be able to make very vibrant, advanced kind of games, the only color mode that the Exist16 library is going to concern itself with is 256 color mode. I'm not really planning on supporting any others. Here's an image of the default Commander X16 256 color palette, and an example of an image that is made using just 3 colors from that palette. Now personally, I am probably not ever going to find that I need to use any custom palettes because the Commander X16s seems to have a very good spread of colors that will pretty much cover my needs. But the Exist16 library and utilities are going to provide support for using custom color palettes if you want to do so. Now, the fact that the images in the X16's memory are formatted like this is relevant to us because it means we can't just take some arbitrary modern full-color image and just shove it into the X16 and expect it to work. And even if you make indexed images with a 256 color palette, whatever image editor that you're using isn't necessarily going to save them in a format that can be understood by the Commander X16. So, the first part of my Exist16 suite is actually a utility, which is an image converter that accepts PNG files and also accepts a palette to index them into, and it will then convert those PNG files into raw indexed data, which can be loaded directly into the Commander X16 for use without modification. So let's go ahead and take a look at the Exist16 image converter. I am, of course, going to have a link to this utility in the video description so that you can make use of it yourself if you want. Now, at present, I am only able to export this utility for use on Windows and Linux computers. So for users who only have access to a Mac computer, I do apologize, but at present I don't have the resources to export it for use on your systems. But if anyone else is able to make a variant of this utility that works on Mac computers, then let me know, and I'll certainly be happy to make it available for use on that platform as well. So that said, the utility will ship as a self-contained executable that should not need any dependencies or any other software to run. So you should be able to just download it, unzip it, and then just run it right out of the gate. Now, the way it works is it has a data folder, and inside the data folder, you're going to put any PNG files that you want it to convert. And right now, we've just got the demo PNG file in here. So if I open this up, and take a look at the demo image, just zoom in a bit, we can see that we basically have what is obviously an adventuring party with a dwarf, a cleric, a wizard, and an elf. And the size of this image is 128 by 128 pixels, and it is full color RGB. And then aside from any PNGs that you want to convert in the data folder, you're also going to want to put your palette, whatever the palette is that you want the converter to use when doing the conversion. By default, it comes with the standard Commander X16 palette. So you can see that it literally is just an image file that has each of the colors as one of its 256 pixels. And if you don't want to use the standard Commander X16 palette, then just make your own image that is like this, except replace each of the colors with whatever color you want in your palette, and then just replace this file with yours. And the converter will use that one instead of the default. And as long as you have the word palette in the file name of the palette that you're using, and it's the only one in the folder, then the converter should automatically pick it up and use it for the conversions. So once you have your palette in place and any images that you wanted to convert, all you do is you just run the executable. A window will briefly pop up and then immediately disappear. And the way that you can tell it worked is you go back in the data folder, and there should be one new file for each of the images that you want converted that has the same file name as the original, except it now has a .img extension, and it's in all uppercase. And if you just copy the resultant image file, .img file, into the assets for use by your Commander X16 program, you should be able to just load them directly into memory and be able to use them verbatim without modification, because it's just a raw series of palette indexes. Or I guess I should say indices, used a proper plural. And that's pretty much all there is to it. It's designed to be a very simple, user-friendly utility. It's pretty much just plug and play. And the way it works is first it looks for an exact match. So if you have any colors in your image that are an exact match with a color from the palette, then it will use that exact index. But if it comes across a color that isn't an exact match, it just tries to find the closest match that it can and uses that one. And it's not a super fancy algorithm or anything. It doesn't like add any dithering to the image or anything like that. It's pretty much just a closest match algorithm. The exact way that the algorithm works isn't really important for the purposes of this discussion, so I'm not going to get into the details of it here, but I will also include the source code of this utility as another download, so that if you want to see how it works, you can, and if you want to apply modifications to the algorithm, you can do that too. Now, let's discuss another consideration with regard to loading and handling our graphics. Most games are likely to have a very large number of images. You probably don't want to have one image per file, because then you would get an explosion of files, which is just kind of messy and disorganized. And on modern systems, there's a fair amount of overhead with opening files, and although I'm not really versed in the details, I would assume the same is true on the Commander X16. So for both organizational reasons and for better efficiency in our code, we're going to want to be able to store multiple assets in a single file. That also means we're going to want to be able to pull particular sections out of a big chunk of graphical data in memory. This presents a conundrum. A typical sprite sheet will have its images laid out like this, so that it's easy for humans to visually parse and edit them. But remember that memory does not really have any concept of dimensionality. So when you read in a file like this into a linear, which is to say one-dimensional series of memory addresses, the sprite sheet is going to get all scrambled, with the graphical data from different images alternating. And this makes grabbing the images we want out of memory trickier. So, the first set of functions in the Exist16 library is for making it easy to do the following. Read an image file, or any other kind of file, but right now we care about graphical data, off of disk and into a bank in HiRAM. Copy a sequential series of data from HiRAM into VRAM, and most importantly, an intuitive function to grab a chunk of image data out of HiRAM and copy it into VRAM based on its position and dimensions in the image, automatically doing the math for you to grab the right addresses out of memory. The math is not really very complicated, But having to do this manually all the time would become very error prone, so having a function to do it for us will make things much simpler. All right, let's go ahead and take a look at some of these functions in action. So here we've got a little project where I ported over just these functions from the Exist16 library. And these functions are contained in mem.c, and of course we have a header file so that other source files will have access to the relevant defines and the functions themselves. So the function signatures, which are the most important thing for the purposes of using the library, are load file to HIRAM, which takes the file name and the bank in HIRAM that you want to load the file into. Copy HIRAM to VRAM, which copies an entire sequential series of data into VRAM out of HIRAM. You give it the VRAM address you want to copy to, the HIRAM bank you want to copy from, and if you don't want to copy from the beginning of the HIRAM bank, you can provide a memory offset to start copying a certain number of bytes into the bank. And finally, the total number of bytes that you want to copy into VRAM. And then, finally and most importantly, copy HIRAM to VRAM partial will just take a rectangular chunk of data, graphical data presumably, although theoretically you could also copy other kinds if you wanted to, from HIRAM into VRAM. So the whole purpose of this is if you have a sprite sheet with multiple images on it, you take one of those particular images, offset by a certain amount and with certain dimensions, grab just that part of the image data and copy it into VRAM. So you have the VRAM address you want to copy to, the HIRAM bank, just as with the previous function. Then you also have an X offset, which is the number of pixels from the left side of the image that you want to start copying from, or bytes, since each pixel in a 256 color image is a byte. The Y offset, which is the vertical number of pixels or bytes that you want to start copying from. The width of the image that you want to copy, the height of the image that you want to copy, or I guess I should say the subset of the image, the width and height of the image subset you want to copy. And then, in order to do the math correctly, the function also requires the width of the entire image that you're copying from. And now we've got a simple little main file just to demonstrate. So obviously we're going to have to pull in our mem.h so that we have access to those functions. And once again, as always, we're going to turn on 320 by 240 display mode. Then we flip on the right bit in the Vera to turn on sprites. We're going to load our testing image, sectest.image, which, if you're wondering, is going to be the same as the demo image that we saw earlier with the when we were seeing the file conversion utility. And then we call our copy HIRAM to VRAM partial. So let's go ahead and break down our call to this function so that we can see an example of how to use it. And if you were wondering how the version of this image looks after it's converted to the Commander X16 256 color palette, well, you're about to find out. Or at least you're going to find out one portrait at a time. So first, we have to give it the memory address in VRAM that we want to copy to. Then we have to give it the bank number in HIRAM that we want it to copy from. Now, this is actually worth a little bit of explanation, because here we are telling the load file to HIRAM function to load the file into bank number 15. And yet, when we're copying HIRAM to VRAM, we're actually copying it from HIRAM bank 16. What's going on? Aren't we off by one here? Aren't we just going to grab a bunch of random junk data? Well, actually, no, we're not. And the reason is because, remember, each bank of HIRAM is only 8 kilobytes. And this is a 128 by 128 pixel image, which is actually 16 kilobytes. So it's not big enough to fit into a single bank in HIRAM. Fortunately, the load file to HIRAM function is smart enough that if the data you're loading spans multiple banks of HIRAM, then it will just automatically do the spillover for you. So since our image data actually occupies two banks in high RAM, 15 and 16. That means we can access either of them when we're pulling the image data out. And as it turns out, this top part of the image is going to correspond to high RAM bank 15, and the bottom part of the image is going to correspond to high RAM bank 16. And each of these is going to be 128 pixels wide and 64 pixels tall. Okay, so with that understanding, we should be able to puzzle out which part of this image it is that we're going to pull. So we are doing an X offset into the image of 64 pixels. So from the left side of the image, we go 64 pixels in. So we're going to be grabbing one of these two, and we are doing a Y offset of 0 pixels, which means from the top of our image data, we're not going to offset downward at all. But remember, we are grabbing the image data out of bank 16, not bank 15, which means we're actually looking at the bottom half of this image. So if we're grabbing the bottom half by getting the second bank, offsetting 64 pixels from the left and 0 pixels down, that means our starting point is going to be the very middle pixel of the image right here when we start copying. And then we tell it we want to copy 64 pixels wide, 64 pixels high, and that the total image width, which remember it requires this in order to do the math correctly when it's determining which sections of memory to grab, is 128 pixels. So we start here, we grab 64 pixels wide, 64 pixels high, and from that we can figure out we're going to grab the portrait of the elf. And we're going to load it into the VRAM image data starting at memory address in hex 4800. Then we have to do our Vera manipulation. Again, I'm not going to explain how this part works because I'm assuming that you went through the tutorials that I mentioned in previous videos, or you just already understand how this works. But what we're going to do is we're going to point to the index of the first sprite in VRAM, and then we're going to set the parameters of the sprite, setting it to 256 color mode, and setting its address so that it's going to point to the address in VRAM where we loaded our subset of the image that we just pulled in. And then we set its X position and its Y position, and make it a 64 by 64 pixel image, and all the other stuff that you manipulate in order to work with sprites using the Vera on the Commander X16. And then we just loop endlessly. All right, so let's go ahead and take a look at what happens when we run this little example. All right, we'll go ahead and build it. Go into the build folder, run it. And there we go. As you can see, it successfully loaded the entire image, copied it into high RAM, and then we successfully used our copy partial function in order to grab just the chunk that we wanted out of memory. And then we use the sprite index 1 to point to the location of this image data in our VRAM and display it on screen. And you can see an example of how the image conversion comes out after you convert it from full color to the Commander X16 256 color palette. I think it does a pretty good job. Personally, I think that this is a very nice 256 color representation of the full color image over here. In general, I'm very pleased with the tests I've done on how well the image converter does converting full color images into the 256 color palette. Okay, so let's just do one more quick demonstration. Let's just change some parameters so that we pull a different portrait out of our image here. So, pop quiz time. How would we change the parameters of this function to, instead of pulling out and displaying the portrait of the elf, let's say we want to display the portrait of the cleric instead. If you want to solve this for yourself, go ahead and pause the video here, come up with your values, and then hit play again to see if you're right. Okay, ready for the answer? 3, 2, 1. All right, so first thing that we're going to have to do is remember, because this image was too big to fit into a single bank of high RAM, we're going to have to go back to bank 15. And that's it. We don't have to update any of the other values because we're already offsetting 64 pixels in, 0 pixels down, grabbing a 64 by 64 pixel image. And, of course, the size of the image hasn't changed. It's still 128 pixels wide. So we just save that change, cd back up into our source directory, build the program again, run it again, and this time, voila, there's our cleric. Okay, I guess there is what looks like is probably a little bit of JPEG artifacting off the side of his head here. So that's the sort of thing that I would clean up if I were going to use this image in an actual game and not just for demonstration. But still, you know, setting aside that little bit of JPEG artifacting, I think this turns out really well after going through the image converter. All right, let's do just one more. So, as just one more example, let's say we want to grab the dwarf instead of the cleric. The way that we would change that is we're still in the same bank in high RAM, bank 15, and all we have to do is change our X offset. So we just change this 64 to a 0 so that we offset starting from the very left side of the image. And that's the only change we have to make. Then we just cd back up, build it again, cd back into the build folder, run it again. And voila! Look at that awesome, badass, cantankerous looking dwarf. He is ready to kick some orc ass. I can't wait to start making an RPG with these characters. It's going to be great. All right, and so with that, we've got a nice set of convenience functions for loading files into high RAM and being able to copy chunks of sprite sheets out of the high RAM into VRAM. Nothing too fancy yet, but nonetheless going to be very convenient for our use. And things are only going to get more interesting from here.